So at the beginning of this chapter, we learned about quantum mechanics, how it explains a lot of properties of elements and certain groups of elements. And then we also learned about where electrons reside in the atom, right? We learned about the quantum numbers and what everything means. Now we can continue to build on those quantum numbers, and we can use them to help describe the electrons that occupy the orbitals in an atom with something called an electron configuration. So this is just a description of the electrons where they are in whatever given atom or element that you're looking at. So you have three different components that make up an electron configuration. You have the principal quantum number, the n value. That is your first value that's the number in front of the letter. Now the letter designates the orbital type. So for example, here we have an s orbital, which if you remember, that's the sphere, corresponds to a certain L value equals 0. And then finally we have a superscript number that designates the number of electrons in that subshell. So in this particular subshell, in this 1s orbital, we have one electron for hydrogen. So this is hydrogen's electron configuration, 1s1. So next we have orbital diagrams, and the way I like to think about orbital diagrams is that they are the visual version of electron configurations. And essentially that's what they are. So we learned, and I was kind of like doing that as a preface to orbital diagrams, but we learned about that analogy, right, with the house and the different levels in the house, and then each room is an orbital, and each room can have 2 electrons, right? And we saw that each room was like a little square, and that was because I kind of wanted to prep you for orbital diagrams. So we use a square, obviously, to represent each orbital, and then we use a half arrow to represent each electron in the orbital. So this half arrow that you see right here spinning up, it's just showing that there's one electron in there. Now whenever you have a paired electron pair, you will have one arrow up and one arrow down, and then anything that's only like by itself, any electron that's by itself is considered unpaired. So before we go into learning more about orbital diagrams, showing you examples, electron configurations, we need to learn some principles and rules. The first is the Aufbau principle, which all it tells us is that as atoms have more and more protons, they will have an electron to match it. That's all it really tells you. And as the number of electrons increases, then you keep filling orbitals in a particular order, which we will talk about. Secondly, we have the Pauli exclusion principle, which tells us that no 2 electrons in an atom may have the exact same 4 quantum numbers. Now you can have up to 3 being the same, but that last one has to be different. So just think of it like, because remember MS is our like bunk bed, think of it like that bed belongs to that electron. No other electron can have that exact same bunk bed, same room, same house. It can have the bottom bunk or the top bunk, whichever one, the opposite one, but it can't have the exact same one. And then finally we have Hund's rule, which tells us that degenerate orbitals, degenerate just means that they have the same energy level, have the lowest energy when the number of electrons having the same spin is maximized. Now this sounds confusing, but I'm going to show you what this means. So here we have an electron configuration for nitrogen. So the way that we fill is you fill the orbital as much as possible. So here we have 1s2, so I'm going to fill that one first. So I filled 1 electron so far, and then I'm going to fill that second one. Next I'm going to fill the 2s2, 2, and then finally, how do I fill these last 3 in these 2p orbitals? Am I going to go like this, like one orbital at a time, or, and I already have the answer up here, but will I go like this? And the answer is you will fill to make it be half filled so that they're all spinning up. Now, the reason for this is because of Hund's rule. So this makes the orbitals have the lowest possible energy whenever the electrons are all having the same spin. So you try to fill them as much as possible before you start pairing. And this just helps the atom be more stable, and it's what it likes. So now we have talked about the different principles and rules that we use to show orbital diagrams and also to properly show electron configurations. So I talked about Aufbau's principle, which just states that as you add protons to the nucleus of an atom, then electrons will match it, and they will fill the orbitals in a certain order. Now, this is the order, and it is all dependent on energy. So the lower the energy the orbital is, that will fill first. So this is the order that they fill in, and it also corresponds to the amount of energy. In general, it will be SPDF, but there are some exceptions that exist, and I just want to point out why. So for example, 3D is higher than 4S. What does this mean in terms of filling? So because 3D is above, and sorry, this line is ugly, is above 4S, that means 4S will fill after 3P, right? That jump is smaller than in comparison to the 3D jump. So orbitals, like, think of them as they're lazy. They want to go whatever is nearest above them. So instead of going to 3D, they're going to go to 4S first because the jump is smaller. So keep that in mind, that this has to do with energy. Now, luckily, we have this nice little diagram that can help you understand this order. You don't have to sit here and pull this particular graph out every single time. But here I want to pose this question. If the 4D orbitals are full, what orbitals will fill next? So I'm going to show you this little diagram. So 4D orbitals, you find it, and then in order to figure out what's going to fill next, you just follow the arrow, right? So here, this little diagram has all the orbitals set up, and these are all the possible orbitals, so it doesn't go further than this. And then the little arrow tells you what fills next, so you just follow it, and you can use this to help you learn and just practice with electron configurations and orbital diagrams. So let's say I'm going to ask you about electron configurations, or to draw an orbital diagram or something, right? How do you get started? You're going to determine how many electrons an atom has, and remember, this is going back to chapter 2. The atomic number is equal to the number of protons. If nothing else is stated about the element, then you can assume that this number of protons is equal to the number of electrons. So for hydrogen, the atomic number is 1. So we can say it has 1 electron. How do we write the electron configuration and the orbital diagram? The electron configuration, you will fill the first orbital possible, which is 1s1, and it only has 1, so you just write the little 1 up there, right? And then for the orbital diagram, you only have 1s orbital, that's it, that one room, and you just fill it. First you draw the arrows going up, and then you start filling down. Next we have helium, and I'm just going to show you some examples. Next we have helium. It has 2, the atomic number is 2, so it has 2 electrons. So the way we fill is, first we look at the very first orbital possible, it's a 1s, and then we have 2 electrons, so we write that superscript 2. If we want to look at the orbital diagram, it's still that one room, and you show that there's 2 electrons by showing the 2 arrows. Here we have lithium, so now this one's getting bigger. We have that 1s2 again filled. We're good with that one. Now what happens next? Once you fill that one up, you will follow this little diagram and see what's next, which is 2s. So here we drew out our 2s orbital, and we drew out that electron within it. So total, you can total the electrons up. Either if you're looking at the orbital diagram, you can just count them up, so 1, 2, and 3. If you're looking at the electron configuration, you can look at the superscripts, so 2 and 1, that's 3, so 3 total electrons. So as the atom gets larger, you're going to have to keep increasing the different types of orbitals, and I'm just following that little diagram that we've been using so far. So, for example, carbon. I'm going to skip through these two. They're just there if you want to look at them. This is for boron and beryllium. So carbon. The atomic number of carbon is 6, so it has 6 electrons, unless, you have some more information about it, right? So it has 6 electrons, and when we write out the electron configuration, we use whatever possible orbitals that we need. We fill up that 1s, so we're done with that one. We fill up that 2s, that's a total of 4 electrons so far. We still have 2 electrons to fill in orbitals. The next 2 will fill in the 2p orbitals. So we drew the 1s orbitals, we drew the 2s orbital, they're singular orbitals. We drew the 1s orbital, the 2s orbital, and then we draw out this 2p orbital. So why does this 2p orbital have 3 little rooms instead of just 1? Because remember, there's 3 different types of p orbitals. There's px, there's py, and then there's pz. And remember that this also corresponds to the ml value for L equals 1. And remember the range for ml is -1, 0, and +1. So that's why there's 3 orbitals for 2p. So we fill, again, based off of Hund's rule, which is to fill, try to half fill it first, and then you start pairing. So that's why you see that it's filled like this versus just pairing them in one of the orbitals. So this is an example of a bigger atom in comparison to what the hydrogen and the helium we just talked about. So here I have an example question, and I'm asking you to determine the element represented by each orbital diagram. So the easiest way to do this, and the thing is, again, keep in mind, I can test you in many different ways. This is in particular one of the easier ways. The easiest way to do this is to just count up the electrons, because remember that the number of electrons is equal to the number of protons. Now, if you have the number of protons, that also tells you the atomic number. And if we have the atomic number, we have the identity of the element. So once we get this figured out, we get the atomic numbers, and then we just look at the periodic table, and that will tell us which element it is. So let's just count these up. So we have 1, 2, 3, 4, 5, 6, 7 electrons. That means we have 7 protons. That means our atomic number is 7. And I'll just write it on the side. Here we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that means 8 protons. Atomic number is 8. And then here we have, this is just increasing, 9p, so 9. And then we have 10 electrons, 10 protons, so the atomic number is 10. Now let's find out which element is represented by each orbital diagram. So I pulled out my periodic table, and now I'm going to look at which element is which. So atomic number 7 is an atomic number, is nitrogen. Atomic number 8 is oxygen. Atomic number 9 is fluorine, and then atomic number 10 is neon. So now we determine what element is represented by each orbital diagram. So we just counted up the electrons within all the orbitals shown